introduction of me. Hello everyone. I'm glad to have a chance to talk to you. Now I'll present about the prevention of oscillatory fast triggering of two parallel GaN-HEMTs. First of all, GaN-HEMTs have excellent performance such as fast switching and low resistance. Thanks to these characteristics, the circuits can achieve the size of compact and high efficiency. So the GaN-HEMTs are expected to be used in high power applications such as EV inverter and high-speed charger. However, GaN-HEMTs also have the disadvantage. This is weak for the large currents. To resolve this, to reduce the current stress, GaN-HEMTs often use the parallel connection. So the GaN-HEMTs are required in parallel connection in high power applications. However, the parallel connections also have the problem. This is called the parallel oscillation. This phenomena is continue turn on and turn off both to parallel GaN-HEMTs. So this circuit shows the double pulse test circuit, which having the parallel connection in the lower side, and this waveform is parallel oscillation. Waveform is when the parallel oscillation occurs. This parallel oscillation, if occurred, it may generate the large switching loss, and it may cause the destruction of the circuit. So we must suppress the parallel oscillation to protect the circuit from breakdown. Now I talk about the mechanism of the parallel oscillation. We consider the only around the two parallel GaN-HEMTs, and we also consider the parasitic components. So if the first the parallel oscillation, the first switching noise flow to the power loop like this pink lines, and due to the imbalance of the parasitic components. The second, the switching noise flow to the gate loop via the CZD and LS, and cause the oscillations if the gate loop frequency close to power loop frequency. So the parallel oscillation is caused by imbalance of the circuit. So to suppress this parallel oscillation, the previous study is proposed the method is to separate the power loop frequency and gate loop frequency. However, this suppression strategy also have the problems. If the circuit size very small, the power loop parasitic inductance and gate loop parasitic inductance are also close, and the CDS and CGS of GaN-HEMTs have the same order from the GaN-HEMT structure. So the power loop frequency and gate loop frequency tend to be comparable. So we must to derive another design guideline if the case of the power loop frequency and gate loop frequency are close. So the purpose of this study is to propose the alternative suppression strategy for parallel oscillation in two parallel GaN-HEMTs when the power loop frequency and gate loop frequency are close. The approach of this study is using the design method of the adjusting another parameter which have the design flexibility instead of the power loop and gate loop parasitic inductances. So now this presentation will follow this progress. progress. So the approach of this study is the refer to the suppression strategy of single GaN-HEMT oscillation to suppression the single GaN-HEMT oscillation. This previous study did this progress. Now, the previous study consider this circuit which having the single GaN-HEMT in the lower side of the double parasitic circuit, and considering the parasitic components, and transform this circuit to the oscillation circuit, and analyzing this oscillation circuit and derive the condition not occur the oscillation, and the suppression condition is derived. This suppression condition means the change this LS and CZD to satisfy these formulas. So we refer the method to transform to oscillation circuit to the double parasitic circuit, and change the changing the ratio of LS and CZD to satisfy this formulas. So now first we derive the equivalent circuit. We did the equivalent circuit transformation to derive the oscillation circuit. First, we consider the double parasitic circuit which have the parallel connection in the lower side, and contain the parasitic components of this circuit, and we also derive this equivalent circuit. Next, we apply the high frequency transformation with using these approximates. We consider the short circuits of the high side diode and the input capacitor and gate driver, and this circuit the parameter of parasitic components having the symmetry structure around the two parallel GaN-HEMTs, and the GaN-HEMTs considered as the current source with the mutual conductance GM, and the high frequency equivalent circuit having the two of the star connection of parasitic inductances. So we apply the star delta transformation to these star connections, and we also derive this circuit, and that circuit have the axis of symmetry in the center of this circuit, and if the parallel oscillation occurred, this having the same amplitude of the two parallel GaN-HEMTs. So if left side GaN-HEMT having the higher voltage, and the right side GaN-HEMT having the lower voltage, the center of this circuit, this points of the axis of the symmetry, on the axis of the symmetry having the zero voltage of each point. So we can consider as the short circuit of this points crossing the axis of the symmetry. So this circuit, the left side and the right side of this symmetry circuit having the same circuit. So we can consider we can be transformed to single GaN-HEMT circuit, and we obtain the simple equivalent circuit. this circuit having the star connection of parasitic inductance at node of A or node of E. So we apply the star delta transformation at this point, and we also derive the final equivalent circuit. So this final equivalent circuit is the equivalent circuit of the oscillation circuit. So next we derive the separation condition with analyzing this final equivalent circuit. This final equivalent circuit is the equivalent to a Barkhausen type oscillation circuit. So we apply the oscillation condition to this circuit and analyzing the not oscillation occurs. We analyze this circuit and we obtain the not occur the oscillation. So we got the separation condition like this. This separation condition having the several ratio of the plastic inductance and the capacitance, but the LDB is a power loop inductance, and the LGB or the dead loop inductance are the constant in this circuit, and the plastic capacitance of GaN-HEMTs are the fixed. So we must to change the LCOM value to satisfy these formulas. So it is important to optimize the design of LCOM and CZD to match the other parameters. So to confirm this method to suppress the oscillatory to suppress the parallel oscillation, we did the experiments. This is a experimental circuit, and this is a PCB. This picture is a PCB. So we did the experiments as following this process. The first, we prepare the 4 PCBs which having the different LCOM values, and adjust the ratio of LCOM and CZD by external capacitor inserting in parallel to the both GaN-HEMTs of the dead terminals and drain terminals. The next, we observe the waveform after turn-off transition, and we confirm the which occur or not occur the parallel oscillation. So we did the experiments with the several ratios of LCOM and CZD. Now I explain about the how to change the common source inductance. The method of this method to change the common source inductance value is changing the position of the through holes at the or the layout of the PCB. These pictures shows in the 4 different circuits or the layouts of the 4 different circuits. The layout A, as showing the layout A, this pink line shows the power loop current, and the blue line shows the dead loop current, and this green area having the common area or the power loop current and the dead loop current. So this green area having the common source inductance. The PCB A having the 76 picohenry of the common source inductance, and the PCB B having the 99 picohenry of the common source inductance. This change made by the most left of the through hole having the dead loop current is flowed, which the did loop current flows. So if this whole position changed, the common area the common area to be larger, so the common source inductance also having the large value. And this PCBC having these structures, so the power loop current flowing the first layer, and did loop also flowing the first layer, and through the upper side of through holes to the fourth layer, and through the fourth layer and to the lower side of the through holes, and the dead loop current for the third layer to the dead driver, like this, and the power loop current for the second layer to the input capacitor. So the common area is these areas. The common area are these areas, and this common having the very long length. So the common source inductance also large value, also having the large value, and the PCBD having the narrow layout of the first layer. So in this points having the large inductance, and also the common source inductance is having the most largest value. So as shown in these pictures, the common source inductance can be changed in limited space. And the result of the experiments, we show the result of the experiments. This graph showing the result of the experiments. The vertical axis shows the value of external capacitor, and the horizontal axis showing the value of the common source inductance. And the circle points showing the three first triggering occurred. These points considered as the parallel oscillation suppressed, and the triangle point shows the 4 to 9 first triggering occurred, but it's not oscillation. And the cross point shows the parallel oscillation occurred. Showing this picture. This red line, this red area showing the area made by the ratio of the parasitic inductance and the parasitic capacitance. So this area satisfies the suppression condition of the parallel oscillation. So now and show the right side of waveform. If sorry, this mistake is if changing the Elcon value by PCB, each PCB, and if nearby the suppression condition, the parallel oscillation is suppressed, and if far from the area of the parallel oscillation of the suppression condition, the parallel oscillation is occurred. So we confirm the usefulness of adjusting the ratio of CGD and common source inductance. So this is the conclusion of this presentation. Thank you for listening.